All right, let's get started, everyone. So hello, welcome to our monthly Stats Central seminar. So for those who don't know, at Stats Central, we offer a bunch of core services that I have in this slide here. So we offer free design advice to all UNSW researchers, as well as free design and analysis advice to HDR students. And we also have free statistical review of any of your grant or test proposals. And we also run some short courses as well as monthly seminars, which is what you're watching right now. And finally, we have partnerships and contracts. If you have any, we offer partnerships and contracts if you have any bigger jobs and you have the money for that. So today is actually the last seminar for this year. The next seminar is going to be next year and late February. So please stay tuned for that. And today we have one of our colleagues, very esteemed colleagues, Elliot Dovis, who's going to be talking about event data. So take it away, Elliot.
Great, thanks, Nixon.
If you could share your screen.
Yeah. You'd think I'd be better at this by now. So hopefully you're seeing my slides. Not hearing any no, so I'm going to assume you can see my slides now. Okay, thanks for having me today. Yeah, so today I want to talk about a few different ways of modeling event data on R with, I suppose, it's not really a definitive sort of lesson in how you should do it. It's really just to hopefully get you thinking a little bit more about your event data that might be collected in various ways. So what do I mean by event data? I guess it's when we're interested in some event. You could think of this as perhaps it's a health outcome. So someone, got better or showed a symptom. Maybe they showed a behavior or had evidence of some sort of behavior, did something, had an experience. Or it could just be like seeing an animal or seeing something. So really, in the most broadest sense, I'm talking about really just recording some kind of categorical thing. And, we're often interested in understanding the occurrence of our event of interest. So we might be interested in it as a frequency or a rate, or the probability or the odds of an event occurring. And we then often want to be able to, say something about how these occurrence rates or probabilities change according to other sort of predictors that we've measured. So things like groupings, other categorical things like maybe treatment groups or other classifications, or continuous measures, things like environmental conditions or dosages. And really, I guess, in this kind of broad sense of looking at event data, we can then also start to think about, well, what do we really mean by rates and probabilities? Is it the rate occurring in population? Is it the rate occurring over time, or the rate occurring in space? So these are all sort of things to start thinking about potentially start thinking about your event data in broad sort of brush terms. And so I guess a good starting point, and in many cases the final point of an analysis of event data, is to use a generalized linear model, which is, basically I guess I'm hoping that you're at least somewhat familiar with a kind of regression style model. That's, I guess, in the simplest case, that's a linear model where we're relating some continuous variable to some other variables, and we can, make sense of those relationships through that model. I guess a generalized linear model kind of gives us a range of different distributions or likelihoods for our response variable to take, which can accommodate these kind of categorical responses, things like events occurring or not, or rates of events occurring, and numbers of times of events occur, and things like that. And so on R, you can do this quite easily in a line or two of code. Here's an example where we've got using just the GLM function. So we start out with specifying how our response relates to our predictors through a formula term here. We have these terms, the response and the predictors, stored in a data frame or table of data where our rows are observational units and our columns are our variables. And then all we need to do to work with a GLM is to specify a suitable distribution that kind of fits to our the type of response variable that we're looking at here. And so then, if you can come with me on maybe just a little bit of a further jump, we have an extension to GLMs that allow random effects in there. So this is sort of, broadly speaking, terms that we're not as interested in, but are necessary to account for, say, correlation across our observational units. So, one of the key assumptions in a generalized linear model or even a just regression model or linear model is that our observations are independent. So we need to, for example, if we've got some measurements over subjects here denoted by this ID term, we need to account for their repeated measurement. They're obviously going to be more correlated sort of within subjects, our observations of some response. And this just allows us to do that. I just wanted to bring this up because this is sort of what I'll be using in some of the examples, but not too much of an extension. If you can make the step from regression models to GLMs to GLMMs, as they're called, you're kind of good to go. And so on R, a really handy way to approach these models is through the GLMM TMB package, which I'm loading in that first line there, and then the GLMM TMB function, which is looking very similar just to your standard GLM function there. And so, yeah, I guess there's a whole range of ways that we might record our event data. Here are a couple of common ones. There's some event in this first case where we've recorded over some kind of observational unit. So we've got our rows of our data correspond to how many times we observe it. So counts of our event occurring, and they're associated with a particular treatment group, in this case being treatment group A or B. And then in our second column there, we have a second way we might record our event data. This time our observational units are at sort of a single trial, if you like. So either the event has happened or not. And so we just record that as a binary thing, the event or no event, pardon me. And again, each of these observational units are associated with a particular treatment group, A or B. And these are two kind of first step common distributions that we might use for these types of data. For count data, the Poisson family distribution is suited to this. And for our binary data, we have a binomial distribution here. There are a whole bunch of other distributions that could be suitable. We'll go and touch on a couple more during this talk, but yeah, I guess I just want to prompt you with this is kind of a starting point usually when someone is presented with either counts or binary data. And one thing I haven't mentioned as well is that what is associated with a generalized linear model is there's also this idea of a link function, though. So there's a particular function associated with each of these distributions that effectively sort of links our formula there. So, how we're saying that the response relates to the predictor variables, it sort of links that to the distribution. It's just, mathematically a necessary thing to be able to incorporate all of these different sort of variable types within a single kind of model framework, giving us lots of power. A little bit tricky behind the scenes mathematically and stuff, but I guess from a practical point of view, it also makes things a little bit tricky in terms of interpreting your outputs. But I'll again touch on that a little bit more. So how do we decide on what's an appropriate distribution we're going to use, or even more broadly, appropriate analysis model for our event data? I guess if you've ever attended another Stat Central seminar or perhaps one of the short courses, you might have heard us talking about a reminder to mind your P's and Q's. I think that's a great starting point. We a suitable analysis approach, and indeed in this case in GLMs, the distribution should arise from your P's, properties of your data. So, how did you record your data? What are the true properties of your data that you're looking at? But also your research question, obviously hugely important. So, I guess from a sort of statistician's point of view, can we frame our research question in terms of the data we have? So we think about these P's and Q's is a good place to start to get to which, for example, distribution we might use. But I'm going to say sometimes we can flout these niceties. As it turns out, for example, binomial and Poisson distributions are closely related. I hope I got to that at the start with the idea about, how you're recording your data. It's really just some kind of event, abstract idea of an event occurring. We might count the times it happens over a certain time or in a population or something, or we might, just mark it as happened or not. So these ideas are really closely related. And so if the sampling units over which we're, measuring our events allow it, we can sometimes be pretty flexible with how we're using these different distributions. And, it can be a little bit tricky, but we can also then often put our sort of model outputs, which answer our research questions, back in terms of our research question. And so I say we're flouting the niceties of minding your P's and Q's, but really, I suppose that I just wanted to sound kind of punk rock. But what I really mean is, I guess, and a big theme of this talk is thinking a little bit more closely about the properties of your data. And as it turns out with event data like this, there are some sort of these properties, these close relations that allow us to be a little bit more flexible in how we're analyzing them. So yeah, now I'd like to go through a couple of examples where, I was able to use these kind of close relationships to swap between things and get around some problems. I'm not suggesting that this is the absolute definitive way to approach these types of problems, but I think it's a handy little way to get you thinking a little bit more about your event data and what it means, and hopefully also to give you some kind of practical guideline, or not guidelines, practical skills to be able to do some of these analyses on R. So I'm going to use mainly the GLM and TMB package, so some modeling, some generalized linear mixed models, and then using estimated marginal means to get sort of our output from our model to answer research questions. Okay, so in this first example, this was a randomized controlled trial where subjects were recruited into the trial after their initial admission to a hospital, where they'd had an event, which then leads to sort of triggers events happening down the track. However, they're quite rare events. I guess the data was recorded as, just whether or not they, so a binary thing of whether or not they experienced this event in tri-monthly periods. They were given a treatment after their baseline reading or a placebo. And, the research question here was, does this treatment sort of reduce your chances of having these adverse events at the various time points sort of beyond? And so, there were just 4 time points in this case, and we didn't want to impose just, a strict linear trend over time. So, estimating either an increasing or decreasing or stable sort of effect of time on the chances of having an adverse effect. So we're considering time categorically here, just estimating time points independently, basically, for a bit more flexibility. Okay, so, given this is just a binary outcome, a good starting point might be a binomial distribution. This is pretty much like what I showed you before. I'm using a model of the binary outcome events. Here I'm specifying that this is a function of treatment and time and the interaction between the two. And so it's really this interaction between the two that's kind of our potential treatment effects here. And I've also got, a random effect in there for the subject IDs because, we're measuring these same subjects over time. So there's going to be an inherent sort of correlation there that we need to account for. But all pretty straightforward stuff. You can fit this model. So when we do that, a important starting point, whenever you're using a model-based approach to answer a research question is to first ask the question, well, is my model a good representation of what the data is actually, what the data actually is? And so we can do that by investigating residual diagnostics. So residuals are really just the differences between our model fit and the observed data. And, they're our model assumptions, the thing that makes, gives validity to the kind of inferences we draw from a model. It sort of reassures us that, if these model assumptions are met, it reassures us that the inference that we make is actually, telling us what we think it is, basically. So things like p-values and confidence intervals have their appropriate interpretations. And so, yeah, those main assumptions really are that our, maybe I'll start with how we can look at these residual diagnostics. So in R, on R, there's the package Dharma is really handy for this, particularly for these categorical family distributions. So things like binomial and Poisson distributions. Why is it helpful? Because the residuals in those cases are a little bit funny to deal with. If you think about it, we've got these sort of categorical responses. So our residuals all get quite squashed up in these categories, and it's harder to look for potential trends in the residuals, which would indicate departures from our model assumptions. And so, yeah, in this Dharma package, we can just use this simulate residuals function for things like binomial and Poisson distribution GLMs that gives us quantile residuals, which under the sort of model assumptions should be roughly normal and should have a homogeneous variance. So, the variability of any of our residuals should be the same, irrespective of where they are in our model fit, basically. And so, yeah, we can use this simulate residuals function. I'm just giving it the model. I'm telling it to simulate 1,000 times here for no particular reason. And this method PIT is just probability inverse transform, which is just our quantile residuals. And we can plot that up, and it gives us these nice diagnostic plots. And so I guess from the get-go, what I would say here is this looks pretty good. Things are looking pretty good here. So the plot on our left is looking at the sort of observed and expected quantiles. For this to be sort of normal, as it should be under this assumption for quantile residuals, our points should all align on that red line that's a sort of one-to-one line. So that's all looking good. And then on our right-hand side, we're really looking, this is essentially just a plot of our model fitted values versus the residuals. So we're looking for things to be no particular trend here, basically. We don't want to see a trend in our residuals based on, how big the model fit is or predictions are. So this is all looking good. There's also a few other tests going on here. You can't really see them that well, but each of these is kind of a behind the scenes test. This is just a normality test, and there's a dispersion test there and stuff. These will actually, as a nice feature of the Dharma package, these will actually flash red when things are looking grim for you. Maybe even when things aren't looking particularly grim. Sometimes they can be a little finicky. So, just if you see a tiny bit of red on this plot doesn't mean the sky is falling in. But yeah, a handy thing to have and a nice tool to be able to make sure that our model is, at least fitting our data, and we can trust or be reassured about the kind of things that conclusions we're drawing from any output from the model. So that's great in this case. We're all looking good there, and that kind of introduces diagnostics, because this is kind of one reason where we might want to swap our distributions if that's not a good fit. But in this case, we're all good. So now another really handy tool on R is to use the package EM mean. So here we want to just get out our expected or average probability estimates over time for each of the treatment groups. And so we can use this EM means function. We just give it the model that we've got, our fitted model that we're reassured is a pretty good fit of the data. And I'm telling it via a kind of another formula here that we want our, in this case, probability or odds of experiencing the event and any of the particular time points. For each treatment group, given each of the different 4 time points. And so I can plot up the results of that, and immediately things look very strange. I don't think that's making too much sense. It's kind of telling us that all of our estimates are from baseline 3 months and everywhere is 0. And then we've got this huge confidence interval at 6 months. So something weird is going on, even though our residual diagnostics were reassuring. So what's going on here? We can look at a summary. So I'm just using the summary function of our model fit here to investigate sort of some other properties of the model fit. And something that jumps out to me immediately is that these standard errors are huge around this time point 3 estimate, and then another one involving time point 3. We've got these really big standard errors. So something weird's going on. And it turns out what is happening here is a phenomenon called complete separation of the event outcomes within a particular stratification of our model. So you can see here when I've just sort of grouped by my time points and treatment groups, and I've summed up the number of events that are happening, you can see that for treatment group A at time point 3, we're actually getting no events occurring. And so that's not necessarily, wrong, an erroneous data point or any kind of outlier necessarily or anything like that. It's just that our binomial family of sort of model does not handle that well. It has because there's kind of no information within that stratifying group, it can't estimate any uncertainty on our parameter estimates here. And so we end up with these huge standard errors. And when we do our EM means, so this is just now looking at the output rather than plotting it up. I was trying to jump straight to the nice fancy output there. We can have a look at what's going on, and you can see that huge uncertainty is propagated to our estimated marginal means. And so you can see here these are asymptotic lower and upper confidence intervals. We can see that they're huge for this time point 3 for treatment group A, where we had just no events occurring. But hang on a second, I guess I want to talk a little bit about what these outputs mean. So we've got these EM means of sort of all negative numbers here. We've got these negative numbers for our confidence intervals. What does that mean? Well, as I mentioned earlier, there's something called a link function for our generalized linear models, which links our, the scale of our formula there to our distribution. So, kind of the scale of what our response sort of means. In this case, we were more interested in sort of probabilities and chances. But you can see here, we've got this little note saying results are given on the logit scale, which logit is the default link function for our binomial distribution. So we can fix that up really easily to make this more meaningful. There's just an argument in our EM means function type. We can just set that to be response, and that will give us our more interpretable, in this case, output of estimated probabilities. And so the confidence intervals here are probabilities again. And so you can see that, the estimated probability for time point 3 at treatment A is, it's estimated to be 0 because there were no events. But the uncertainty around that is that it could be as low as 0 or as high as certain. So, things not really giving us any information there. And we really wanted this, to be able to answer our research question, we wanted interval estimates, say, of our outcomes at our time points. So there's a few different, we still need to fix this complete separation problem. So there's a few different ways that we could do this, but, given the theme of this talk, I'd like to approach it by considering, what these events mean and potentially changing our scope to be a different distribution family. And so it turns out in this particular case, the research question was really interested in time points 3 and 4. Time point 2 was not as interesting. We've also got really rare events. We've got quite a few subjects in this. I think it's over 100 subjects. And so we can actually just aggregate our, counts of our events happening in time points 2 and 3 and model the user model of counts using a Poisson distribution. So we're effectively, approximating our binomial with a Poisson distribution here. And so we can do this in R pretty easily. So I'm just using the forcats thing, which kind of gives us some capabilities to rearrange categorical variables. So here I'm creating new time points where I'm just saying that time points 2 and 3 are now just going to be their own new time point. And I'm going to then just sort of aggregate up our data into counts. So for time points 1 and 4, this is just considering, you know, it will just be a count of 1 where people have had an event or 0 otherwise. But now we're going to, you know, count up all of the events for each person that happened in time point 2 and 3. And so now we're just using basically the same model, except our response is now counts. We're using our, you know, newly aggregated count data, and we're using a Poisson distribution. So same thing again here. We can get our estimated marginal means out. We're saying type equals response. In this case, it's giving us a rate because this is the kind of scale of our response variable for a Poisson distribution. And you can see there that now we actually are able to estimate, you know, the uncertainty around our rates. And in this particular case, our rates are actually a pretty decent approximation of our, you know, probability of these things happening. And so we should check the residuals again, because, you know, if that's not a good fit, then we'd be quite concerned about any, you know, our estimates of uncertainty might be way off here. So we can do that again in the same way. And, you know, things haven't changed all that much. Things are looking pretty good. So we are okay to go on. Great. And so we can plot up the results. We now have, you know, an estimated rate of event at baseline, sort of 3 plus 6 months and a 9-month time. Which is kind of what we wanted. Obviously, you know, we now our 3 and 6 month time period is sort of over a larger amount of time, so we expect to have a kind of higher rate over, you know, a not comparable rate to the 9-month tri-monthly sort of period. So I think in this particular case, the researchers wanted a sort of estimate of the 6-month tri-monthly rate and the 9-month to sort of look across that. One way we can do that from this model, if we can make the assumption that, you know, okay, well, we've got these estimates of the rate across 3 and 6 months. If we want to just separate them out to take a kind of average effectively, we can use an offset term in our model. And so this is just really, I wanted to just do this to show you how this works for count-based sort of regression. So things like a Poisson or negative binomial. This basically just sets the denominator of our rate. So it's we now have the expected number per unit of our offset term. And so we can do this on R pretty easily. Now I'm just adding a time length sort of variable to our count data set. So it's just going to be 2 when we're in our sort of joined time period, or 1 otherwise, and I'm going to times it by 3 months. So it's now just a monthly sort of, it's a measure of months. And then we just add into our formula in this case, a term that's sort of wrapped in an offset function. And we do need to put this, you know, through our link function. So I know that in this case, the link function for a Poisson is just a log link. And so we just take the log of the time length. And then I guess just to showcase in EM means how we can handle that again, we have this handy at argument in the function. So we can give a list of variables in our model, and we can specify, you know, at what values we want our output, our estimated sort of outcomes to be at. And so here I'm just saying I want it to be all as if we are just looking at a 3-month period. And we can plot up the results, and, you know, that brings it our 6-month results. It's kind of, you know, not exactly that. It's an average across the two, but it's back on a sort of scale that's more comparable to our 9 months. So yeah, that was an idea around jumping between distributions to be able to, you know, get around a bit of a problem that we had in analyzing it just in the original way we came to it. I guess the conclusion here might be that you know, while the treatment A did lead to sort of fewer of these adverse events. It's sort of by 9 months, maybe that effect had worn off or something along those lines. But yeah, so let's jump into another example. This is an example where, similar kind of setup. So this data was collected where it was just counting sort of mice doing something that they were sort of tested on, and it was looking at how often these gene-edited mice did it when they were given either a placebo or a treatment. So it's asking the question of, is there a difference in the number of events that occur between these treatment groups over time? Again, I suppose the gene editing thing was expecting to make this harder and harder, and the treatment was seeing, the question was really asking, is the treatment mitigating that effect of the gene editing? And so a similar setup again, where we've got the 4 time points. These are just 28-day periods, and we're going to consider factor time here. And there was also age of the mouse in weeks, where they wanted to control for this in the model. And so again, pretty similar situation. We're going to, given we've just started out with counts, maybe it was in the SAP that we were going to do +on regression on this. And so we might start there. That seems a reasonable approach. I guess this time in my formula, I'm saying it's a function, counts or the rate of counts are a function of age plus this treatment time and their interaction effect. And again, I'm accounting for IDs of the individual mice, so they're being repeatedly measured over time. And so we can check the diagnostics, and here is an example of where things are going awry. And you can see Dharma is spitting out some red things there. Things are not looking good. You can see that our quantile residual now is kind of bending like a banana off our one-to-one line. We're definitely seeing some kind of trend here. It kind of looks like, as our model fits get bigger, the residuals all tend to kind of converge. So yeah, something's going on here. Certainly wouldn't proceed with any kind of inference from this model from that. Oops. And so yeah, maybe there's some kind of dispersion going on. So overall under dispersion is when things get more or less variable depending on what our mean of our model fit is doing. So we could try a generalized Poisson distribution. This just effectively kind of is a more flexible approach, has an extra parameter for dispersion. We specify that with just gen Poisson in GLM and TMB. We can check the residuals again. It turns out it did nothing. And in fact, I think if I look back, maybe I could have noticed this. This, you can't see this really in this plot, but this is the dispersion test wasn't red. When I try and estimate dispersion, it actually comes up with that's red as well. So that's not going to solve our problem here. There is kind of an sort of implied upper limit that wasn't necessarily there in the data when we first look at it. But these counts can really only occur once per day within each of the 28-day periods. So yeah, there's this kind of upper limit on the counts. We can add that into the data, just same for all of them, days equals 28. And we can, again, add it in as our offset like we did last time. Maybe this will help things. No, it doesn't. We're still in a bit of trouble here. So something's going on with this kind of, by approaching this count data, or is it really count data, by a Poisson distribution. So what if we consider instead each day being just a binary sort of variable? So each day is kind of like a Bernoulli, what we call a Bernoulli trial. It's either a success or a failure of these events happening. And so here is another way we can model that on R, is to specify our response as this cbind function just combines columns. So we've got a column that is our sort of number of successes, and then I'm setting the second column needs to be the number of failures that occurred in each of our observational units, our rows of our data. So I'm just doing days minus the count is our number of not successful events happening. And the same model thing, but we're setting it as binomial. Again, we can check the residual diagnostics, and lo and behold, things are not looking any better, which is a bit of a disappointment. But we are now still getting this dispersion test is coming up as, there's potentially significant dispersion here. And we can start to see that things are kind of getting more variable, maybe at this upper sort of quantiles of our standardized residuals. Maybe we're having a bit of over dispersion here. So perhaps our last hope might be a beta binomial distribution in this case. So it's kind of like the equivalent of a negative binomial as compared to a Poisson distribution. There's this additional parameter to handle over dispersion. And so we just specify a beta binomial distribution. We can get an estimate of the sort of dispersion parameter out. This is just using this conf_int function, just gives us our estimates from our model in GLM-MTMB with confidence intervals around them. So, an interval estimate for them. And sigma is the name of the dispersion parameter here. And you can see this is kind of, higher than 0. As this parameter tends to 0, this tends to just a standard binomial distribution. So yeah, there could be some over dispersion going on here. And indeed, when we check the diagnostics, things are finally looking reasonable, which is great. Okay, so now we've got a model that's at least adhering to the assumptions that we require to be able to perform inference or draw conclusions from our model output. We can proceed. And so in this particular case, the researchers were interested in a treatment effect for sort of 10-week-old mice. So again, we can use that at argument in the EM means function, just setting age to be 10, and it'll make these predict these sort of expected probabilities out at each of our study periods and treatment groups. So you can see here, there's not really looking like there's too much evidence of a difference, although, maybe this treatment group 2, so perhaps they received the treatment and that they're, we've consistently kind of estimated, at least in terms of point estimates, a little bit higher, but there's not really too much support for a strong difference there. But again, we're kind of on the scale of estimated daily probability of sort of having this event occur or completing this task or whatever it was. That wasn't really the original research question. They were really interested in what about the differences in the number of events per, study period. So this is really asking for pairwise comparisons of treatment groups within each week. And we can luckily get this out of our EM means object pretty easily. We can use the pairs function, and I want to just, again, use that conf_int function, which is really handy to get my confidence intervals for any sort of pairwise comparisons that we're doing here. And so, yeah, I can get this out here. But again, we're still on this odds ratio scale now. Odds ratio, that's something I haven't even really talked about today. Maybe doesn't make too much sense in terms of, we're trying to ask what are the differences in the number of days events. So this is really just looking at the ratio of the odds. So, if it's smaller than 1, things are less likely for the numerator, which is treatment group 1 here, and more likely for the denominator. But yeah, people, if you've got a research question that's framed in terms of the data in this way, number of days or events that are different, we want to get back to that. So we can't really do that actually with odds ratios directly here. We can't estimate those different numbers of expected events. So we have to come up with a custom contrast for the differences in probabilities here, which is getting a little bit more fiddly. But yeah, I guess the main point here I want to show is that, even if things are looking grim in terms of you've gone out of your way to change a distribution and you're suddenly working with odds ratios and things like that, you don't have to lose hope. There are ways to get back to kind of at least framing things in terms of your original question. And so we can do that by creating a custom contrast. This is just looking at probability differences. So here I'm just saying that this is just going to be across my treatment groups. If you recall, I'm looking at treatment effects by the different time groups, conditional on age, which I've set to 10. Here I'm saying that I want to minus treatment 1 and plus treatment 2. So this is looking at the difference between treatment 2 and treatment 1 that way, like treatment 2 minus treatment 1, the day is different. Then I need to just wrap my EM object in this regrid function, which basically just, tells it to watch out for the link function and handle it properly up in this case. And then I'm just looking at a contrast, and I've got my custom contrast here. And then I can, get out my confidence intervals or sort of estimates of the difference in daily probability of the event occurring and my confidence intervals. And so then from there, it's pretty simple. I can just multiply the probabilities and the confidence interval ends to get the kind of confidence interval for my expected number of different numbers of events in each study period. So again, not telling us too much different here, in terms of the uncertainty on these estimates. You can see that they're all crossing zero difference. So there's no strong evidence for potential treatment difference here. However, it's still showing us, well, we're getting, we'd estimate it is quite close to being above zero for our final time point sort of thing. And I think we saw that in the last one. And this happily sits within the realm of our, original research question. So that's, kind of the couple of examples I wanted to show today. And yeah, again, I didn't really mean this to be a definitive way to approach any of these problems, but really just to, get you thinking a little bit more about how these event sort of data are related and how you might be able to flexibly analyze them. It's, I guess I've come into situations where, I've had situations where there's an SAP written and they know they're collecting sort of binary data, and so it's said it's going to analyze it in this way. But given these flexibilities, and in certain cases where you can jump between the two, you might need to for model assumption reasons or other problems. So just thinking about that, I guess, is a pretty good thing to have up your sleeve when you're considering event data. I guess typically, the more granular you can record your event occurrence is the better. It's generally easier to aggregate to coarser scales than to go down to finer ones. So it gives you kind of more options for appropriate analysis approaches. But yeah, I guess just to recap, I showed you that example of going from binomial to Poisson to avoid complete separation there when we had quite rare events and decent enough numbers of subjects, and an example where we went from a Poisson to a beta binomial distribution to just get better distributional assumptions when we had these bounded sort of counts. And so, hopefully I've also shown you a few, not too daunting ways of being able to get the sort of outputs you want from a model when you're approaching an analysis in a model-based way. Using that EM means package is super handy and helpful. And you can also transform your outputs to match your research question, so you don't have to go revise your research question, maybe that's in a published SAP or something like that. And so a couple of things that I didn't really touch on today, which is also really interesting, is when you talk about events occurring over continuous time or space. So that's, I'm particularly interested in point patterns in time and space. These can be modeled using point process models, which are, again, a closely related thing, kind of could be considered a data generating process for some of these other event data types. But they're really interesting too if you have the time to look into them. There's also time to event data, which is typically analyzed in a sort of survival analysis framework. And it turns out that the Cox proportional hazards model, for example, is actually really closely related to a Poisson process model. So there's in these types of data, there's a lot of kind of relationship and similarities there that are fun to think about. And if you think a little bit more about these properties of your data, hopefully you have all the tools you need to be able to analyze it in an appropriate way. And I'll leave it there and take any questions if there are any.